question about filters. This is a very simple one. So find the transfer function of the following circuits. For this circuits, you can see a voltage source is across these two impedance in series, and the output voltage is across the capacitor. Okay, so it's a voltage divider. So the output gonna equals to input multiply with this impedance over the sum of the two impedance. Okay, so let me write this very specifically. So V out gonna equals to V in multiply with ZC over ZR plus ZC, two impedance. Okay, so the transfer function is defined as output over input. So output over input put in here is just ZC over ZR plus ZC. Okay, that's two impedance voltage divider. And the impedance for this capacitor is 1 over SC, and the total is R plus 1 over SC. Okay, we combine some terms, so we move some terms like this, then we have this one. Okay, I'll put you here. For B, the similar thing. R, this time output voltage is across this resistor plus R over R plus SL. Okay, this is SL. Simplify, you got this. All right, so the part C, so these are the part C. Okay, for part C, create two different circuit that have the transfer function of the following ones. Okay, so basically we want to make that the top one 1 over RC equals to 1000. That's for this one. And you can see we have all kinds of combination for R and C, but if you choose from a certain table, then you will see if R is fixed, then C is kind of fixed. Same thing here. So we want this R over L equals to 1000. Then if R is 10, then L is this 10 millihenry. Okay, that's the first question in week 12. And for this one, very similar. Okay, so again, voltage divider R over R plus 1 SC. This one is SL over R plus SL. Okay, again, if you want to have the certain transfer function, then if you fix one parameter like R, then you can find the parameter for the rest. Very simple. Okay, sorry. For the third one is a active filter. Okay, so there is op amp here. The strategy is still, so the transfer function is outputs divided by input. Okay, but for this op amp active filter, we have this kind of equation, so minus ZF over ZI. So ZF is a feedback impedance, ZF on the top, and here is the ZI, okay, input impedance. So ZF is 1 over SC, I call it SC2, in parallel with R2, okay, and then you do the math, you got that one. ZI input impedance is just this two impedance add together, you got that one, okay, and HS simply is negative ZF over ZI, then you got this one, right? And the 0 and pose, find 0 and pose. So 0 is the root that makes the numerator 0, which is the 0 is equal to 0. Okay, the pose is the roots which make the denominator equal to 0. So S equals to negative 25 or negative 125. That's it. Okay, that's for week 12. And for week 13, we continue on filters. Okay, we still work on filters. We have this kind of filter. All right. We want to find the transfer function. Again, is a voltage divider. So the input voltage cross 1, 2, 3 impedance. Output is only cross 1 impedance. So the voltage divider here is R over SL plus R and plus RL. Okay, this is RL here, so three of them. And then we can collect terms. We got something look like this. All right. So this is not an ordinary um, circuits. So we can't just use that given equation to find, for example, the cutoff frequency. We're going to prove that later, okay? For B, so at what frequency will the magnitude Hj omega be maximum? First, we find the expression for Hj omega, which is very simple. We just have this S expression, then replace S with j omega. So we bring it into frequency domain. Then the magnitude of this transfer function, because there is a numerator and denominator, is equals to the numerator magnitude divided by the denominator magnitude. And for the numerator, it's just a real number. R is a real number. L is inductance is a real number. So real number magnitude is still real number. This imaginary number like a plus jb form is a complex number. For complex number, we have a squared plus b squared square root. Okay, and you can see for this one, when omega, the frequency can be 0 to infinite, any frequency, right? So the question is, in which frequency this magnitude, this one, or this one, the same, right? Got the maximum value, all right? A constant divided by a constant plus a variable. We want the denominator as small as possible to make the overall thing maximum. So how to make the denominators as small as possible? These are the fixed numbers. So we want to choose omega equal to 0. So we got an overall maximum value. All right. And then let's find out if omega equals 0, how much this magnitude is when omega equals 0. So you plug omega equal to 0, then you got R over R plus RL. That's the maximum the maximum gain. You can see is not 1. Okay. When you consider the in the real world, the inductor will have a resistance associated with it. So it's not an ideal case. So in that case, you can't get a 1 as the maximum gain. All right. For D, what frequency will the magnitude of that transfer function equals to its maximum value divided by root 2? If you're familiar with the concept of cutoff frequency, actually at that frequency, particular frequency, the magnitude is actually 1 over root 2. So the question is actually ask us to find the expression for cutoff frequency. All right. First, we know the maximum magnitude, we just got it, is R over R plus RL. Multiply with 1 over 1 over root 2. That is the new magnitude for that particular frequency. Okay. The expression, the general expression is this. We just replace the omega with omega c. All right. And we know the value is this one. All right. So there are only one unknown, which is omega c. We can multiply both sides to find the result. So omega c actually equal to R plus RL over L. Okay. The last part for E, if we're given some numbers, like for this resistance, RL, and for the inductor, and for this RL is actually from a previous question, so it's missing here, so 1200. If you know all of them, then omega c can be calculated. Omega c is R is 1200 plus 300 divided by the L 0.05, then we got this cutoff frequency. Okay, and then hj0, which is omega equal to 0. We already know that. That's the maximum magnitude. And then that's 0.8. You can see is not 1, it's less than 1 because we have some kind of RL there. Okay, it's not ideal case. And at cutoff frequency is not 1 over root 2, is actually something like this. So you plug in numbers. Um, this is, we know omega c equal to this. Okay, and then you got this number, right? And for 0.2 omega c, because you already know omega c, 0.2 omega c. Okay, then you can just plug in numbers because you know the frequencies look like this. Okay, hj omega is look like this. So hj omega look like this. Then you just plug in numbers. Then you put j omega here. Okay, that's the j omega. Then you find this one. There's this new omega here. Then you find the last one. All right. What's next? All right. So in this one, use a inductor to design a low pass filter. All right. So we have a infinite combination of inductor and resistor, but here we give a inductor, then you can find that particular resistor to work with it to get this cutoff frequency. All right, so 2 pi f is this 1600 radians per second, then the frequency just this 1 omega over 2 pi, then we got this frequency. And for B, we know that omega c is equal to R over L. So this is kind of like ideal low pass filters. And omega c, this R is unknown and L is known. So R is 16. All right. And assume the blue one is the filter we just designed, 16, and that's the inductor. And assume that the cutoff frequency cannot decrease by more than 10%. So it can be 0.9 of the original frequency. Cannot be lower than that. What is the smallest value of the load resistance? That means the largest load, right? Small resistance means large load that can be connected across the output terminal of the filter. Okay, the red one is the load. Okay, and the new cutoff frequency of this new circuit is this two impedance, two resistor combined in parallel become the R hat. Okay, so the new frequency equal to R hat over L. And we know the frequency can be 0.9 of the original value, and the inductor doesn't change, so we can find the R hat is 14.4 omega. And this one equals to 16 in parallel with RL, okay? Then there are only one unknown, which is the RL, then we can figure out it's the 144. Okay? Then the last part, if the resistor found in C, found here, is connected across the output terminal, what is the magnitude of Hj omega 1 omega equal to 0? So we got the new R here, and this is actually S plus that R, J omega L. Sorry, this is a voltage divider again. Okay, this is voltage divider. SL plus that R hat. Then when omega equal to 0, then the magnitude just 1. Okay, final one. Okay, in this one, let me enlarge this one. So we have RLC circuits. Okay, RLC circuits. We want to find the transfer function for this one. Again and again, this is a voltage divider. So the output voltage across this one. So SL over R plus 1 over SC and plus SL. Okay, voltage divider. Then we clear terms, do some changes. We got this one. Part B, find the magnitude of the transfer function in part A for very low frequency. So we just replace S here with J omega. Okay, then we will find when J omega equals to or when omega equal to approach to 0, so the thing becomes, so these are the zeros. So this actually is 0. So it's actually 0 over 1 over LC, which makes the magnitude 0. So the lower frequency being stopped. But higher frequency, which is part C, you can see for j omega when the omega equals to infinite, and this constant become not important. This is not important compared to s squared, so it becomes s squared over s squared, which is 1. Okay, so this is a high pass filter, very obvious. So for E, suppose we know the values for those components, for all three components, calculate the cutoff frequency of this filter, that is the frequency at which the magnitude of the transfer function is 1 over root 2. Okay, so it's, again, we gave the transfer function, replaced s with j omega, we got the transfer function, and we can um, keep working on this, so everything is regarded to omega. All right, and things, the R and L is being given and L and C being given, then we can replace those symbols with numbers. Then we got this hj omega, the transfer function equals to this. There are only a variable is omega. Then at a particular frequency, so the omega can be anything, 0 to infinite. 1 omega equal to omega c, which is the cutoff frequency. Just replace that. We find the magnitude. So on the top, magnitude just omega c squared because it's a real number. On the bottom, a plus jb form, again, a squared plus b squared square root equals to 1 over root 2. Then you square both sides and do the math, you will find that cutoff frequency. All right. Again, I think you see the pattern here for all the filter questions. You need to do voltage divider, very simple. Okay, except the active filter. Okay, you have a special equation for that, which is negative ZF over ZI. All right, so I will stop here. This is all for the filter part.